Good morning, I'm on site here at Embedded World 2022 and joining me today is Arndt from onsemi. So thank you very much for joining me today.
Thanks for having me.
Now we're going to be talking about the first of onsemi's IEEE 802.3CG compliant 10-base T1S devices. So before we begin, could you start by explaining what the IEEE 802.3CG standard is?
Yes, I can, Paige. The 802.3CG is an extension to the already existing Ethernet standard. That's a standard around about 5,600 pages long, and it defines everything around Ethernet. While the CG standard, like I said, is an addition to it, took care of of the lower end of the Ethernet spectrum. It's defining two different Ethernet standards or physical layer standards based around single pair 10 megabit. So there's an L standard that can cover 1,000 meters. What we looked at is the T1S, the short range standard. It's a multi-drop system where we can cover. The standard says round about 25 meters with 8 stations. We can show that we can do more than that.
Okay.
But anyway, it's a multi-drop setup, basically designed to save you wiring, because you have a bus wire and then you can basically tap your stations into it rather than having to go point to point to a switch, which is basically doubling the number of ports. That's what they defined. And they found, this being multi-drop, they found that you have to share the bandwidth, so they defined some mechanisms to basically make that easier for the applications. That's really what it comes down to.
Right, brilliant, fantastic. Now, the NCN260110 device is an 802.3CG compliant Ethernet transceiver. So could you explain some of its features for us?
So before we begin with that, it's what we have to point out. It's a so-called MAC-PHY device. It combines two of the Ethernet layers in a single device. So it brings the physical layer, which is the base layer that basically gives you access to the actual wire, what the IEEE calls the medium. Plus the media access controller that basically allows host computers to basically access, go in with like predefined Ethernet frames, and these two functions basically take care of the rest. That's one of the features, is that it's using the Open Alliance protocol over an SPI interface. It has to run in the range of 15 megahertz to give you the full performance. With that, you can actually hook it to microcontrollers that haven't particularly been built for Ethernet, because that MAC function that you would normally need in a controller or a microcontroller is now integrated into the MAC-PHY device. You can use low-cost controllers as long as they have an SPI interface. Connect these two, do the rest in software, give it a TCP/IP stack, and you have a running Ethernet node. That's one of the features. We've also implemented the optional PLCA feature, which stands for physical layer collision avoidance, that helps you with higher utilization rates. So if you figure this is going to be a half duplex device, you have multiple stations on the net. So you can have a situation where you have more than one station trying to talk. If they do the classical Ethernet way, they would create we call it a collision. Two sending at the same, it's like two people speaking at the same time. Right, you get a collision, and then what typical Ethernet would do, they use the CSMA-CD algorithm, which stands for carrier sense multiple access, and the CD stands for for collision detection. So they would detect that collision, and they would all back off. They would stop sending, and they wait an arbitrary time, like a random time, and then they will go back on and try again, and that collision could happen again, right? And then they double the time, they go back and forth and back and forth. Eventually they give up if they don't find access to the media. What that does to your actual Ethernet link is you can basically utilize it up to 30%, saying 3 megabit of a constant data rate, and then you start seeing issues with the collision detection if you have more than one station talking. The IEEE found a solution for this, which they call physical layer collision avoidance. It happens on the PHY, on the lowest level, so it's transparent to the upper layers. They don't even have to know about it. And it's a round-robin arbitration. I would not tell too many details. It's basically saying you have a head node that coordinates the entire program. Every node gets a certain ID, and then there's transmit opportunities that get passed from one to the next. And the one station that has the transmit opportunity is allowed to send exactly one Ethernet frame, and then it has to let go and basically let the other stations do their communication. What that is a fair share arbitration. So per round, per PLCA round, every station gets to send. So there's no blockage. There's, collision is entirely avoided that way. That gives you the chance to utilize your link to almost the theoretical maximum. We're showing an application on our booth in the demo where we have a tiny little arcade game that runs on top of a base load that we generate of 80%. So we're running 80% of a load, and we're still able to fluently play the game because we have that PLCA feature enabled. That's pretty much what it comes down to. We have we can get to longer reaches by a feature that we call enhanced noise immunity, ENI. And it helps with receiving data at very, very high noise levels. Basically, way over the noise level that the IEEE, sets as a limit, as a lower limit. We can go. We can communicate with the data eye almost closed, and we're still able to decode the packets. That's going to help with the number of stations that we could set on the network. It's going to help in very noisy environments where we have noise levels above 700 millivolts, where the actual signal is 1,000. And it's also going to help to extend the range. So the demo we show in our booth is showing 65 meters, where the standard says 25. So we're more than 2x the distance that we can cover. Right.
Yeah, that's a great range of features there. So let's focus on one of the points you mentioned in particular, which is the integration of the MAC with the physical layer. Yeah. So why in particular is this beneficial to the developer?
It's going to enable you to use very, very low cost MCUs that haven't been designed with Ethernet connectivity in mind. Yeah. You could now use those and think of very small sensors or something like this, where we want to put something in a very small footprint. You could use our 4x4 millimeter device and pair it with a very small footprint, low cost MCU, probably on the other side of the PCB, and come with a footprint that's less than a square centimeter. So that we could integrate this in push buttons or like your temperature sensors, and turn a normal sensor into an intelligent sensor node that you can integrate into your Ethernet environment. Yeah. So everyone could see the sensor, and you can spread the data to whoever wants to get that information.
Yeah, fantastic.
It's going to give you more flexibility if you use a wiring scheme like this. So if you had a push button like this set up in a cabinet, for instance. Yeah. You could reconfigure its function without having to touch the wiring. Yeah. That's one of the key benefits there, right?
Yeah, that sounds great.
Yeah.
So you've mentioned previously that the device primarily targets sort of the industrial market, with one of the use cases being in-cabinet wiring. Can you explain how the device works in this particular application?
Yeah, so in a classical in-cabinet wiring that you see today in an industrial environment, you typically have I/O controllers, and then you have circuit breakers, motor starters, contactors, and a bunch of input devices that the industry calls the pilot devices. This could be gauges on the front of the door, or push buttons and stuff like that. And in that typical environment today, you would do from the I/O controller to all these devices, and then you would do a point-to-point connection with just a single wire. It takes a trained technician around about 6 minutes to install one of those wires. Okay. And there's hundreds of these wires in these cabinets. So it's an error-prone work. You have to document where the wires go. If you have to repair or make changes, it's a hassle touching this again once it's installed. If you could do away with this, it's called a marshalling cabinet. It's actually doing the cross connections between those. If you can do away with that connectivity and replace it by a single bus system like what T1S actually is, you would just run one wire across your cabinet and just basically tap to all the devices that have an interest to talk. Which basically reduces the amount of installation you have to do. You're going from days or hours to minutes, and is reducing the amount of wires you run in the cabinet. And even if you have to do a repair, like you have an issue with your wiring, the easiest approach is you rip the entire thing out and replace it with one single new wire, and you're ready to go. If you want to reconfigure this and you have your, if you have your devices as intelligent nodes in Ethernet, you can basically reconfigure it using software. You don't have to touch the wiring at all at the end. So we see a clear benefit for this technology in this particular application. It'll help you to reduce your wiring effort by 70%. That's where the actual cost saving comes into the game.
That's a huge number.
Yes.
Such a fantastic application. So what other applications are you expecting to see once customers start using the device?
I think what we primarily want, we want the customers to use the devices, and we want them to come up with ideas on what they can do with it. We've identified a bunch of other use cases. One of them is in building controls or building automation. Think of an escalator. You could have, a passenger or detection in the escalator. Say we can stop it if nobody's on the escalator. So you'd have a sensor on the top, you had a sensor on the button, and then you could basically run a bunch of sensors along that 30-meter escalator by just a single wire, and take care that way. Or an elevator, for instance, could be another nice application where you have a lot of functionality inside the carriage in an elevator. It's all short range. It's like an elevator is like 5 by 5 by 5 meters if you have a huge one. So you can easily cover that with 25 meters of cable, or like 50 what we can achieve. So you can, you have the chance to reconfigure your panel on the fly. You could probably exchange this by a touch screen, and you can run the surveillance camera. Even the audio could run over this. So everything that's now wired point to point with a lot of effort, you could replace it by a bus system, like similar to the use case we see in the in-cabinet. It's just taking that idea to other applications. For sure, we know there's life in automotive. Eventually, our device today is an industrial part. But like I said, the best for users is just like take it, try it, and see what they can do with it. There's limitless applications that that our user base could think of, I think.
Yeah, it'd be great to see what applications do come out.
That's what we're excited about.
Yeah, definitely. So seeing as this is a new device, what are your expectations for the use of this device? How do you see it evolving in the future? What's the next step?
Well, we have an evaluation kit available now, so people can order this evaluation kit and start playing with it. We give them some example software that gets them started, so they can build on top of that. We have a basic solution running under Linux. We have a basic solution or an example running on FreeRTOS. We have a solution running on what we call lightweight IP as a bare metal implementation. This is all examples. We don't give them away as reference designs because we're not a software company. No. We're just giving this to get people started, and from there, like you said earlier, we just want people to have a look at it and figure out what they can do with it.
Yeah. Right. Fantastic. I mean, you've covered some of the points for my last question, but how easy is it for users to get started with the device? I mean, from what you've just said, it is literally an out-of-the-box. It's
not 100% out of the box. So, what we give them is just, it's actually 2 boards. Okay. We call this evaluation kit that they can use and bundle it with the Raspberry Pi that they have to bring themselves.
Right. Okay.
Or they can just order the evaluation board standalone. If they said, I don't care about a Raspberry Pi, I would just want to hook it to a microcontroller. We have a standard Digiland SPI connector on it. So a lot of boards that you can buy from different companies, like development kits, have that connector. So you can just basically plug them together. And then you can start with these software examples that we give them. So I'd say in a matter of like a couple of hours, they would get the first ping out of these devices, and then they would immediately see what they can do with it. Yeah. So if you have the stack up and running, you just can take your own application, plug to the sockets of the software on top, and get a running system that way. Yeah,
that's still brilliant. Yeah, so well, thank you very much for your insights on the new device, and I'm very excited to see where it goes in the future.
So are we. Thank you.
Fantastic. Enjoy the rest of the show.
Thanks.
Thank you.